Okay, welcome back. And now we're going to do a proof of Rolle's theorem. Okay, so in doing the proof, there are going to be three cases that we're going to have to deal with. Okay, so first of all, let's assume that we're dealing with, well, let's suppose f is continuous over the closed interval AB and differentiable over the open interval AB. Let f of A equal f of B. So now there's three cases that we're going to have to consider. Okay? Case one is that we're dealing with a constant function. Okay? And we're going to say that f of x is equal to k for all x in the interval a comma b. Okay, now, for that case, if f of x is equal to k for all x in the open interval AB, then guess what? We have a horizontal line because, again, we're letting f of A equal f of B. So if f of x equals k, so again, if f of x equals k for all x in the open interval AB, then f prime of x equals 0 for all, for all x in AB, right? Because so this is the case that we're dealing with the horizontal line, okay? Okay, that's it for that case. Case two is we're dealing with the fact that there exists an x, okay? So case two is, let's say there exists an x in the open interval AB such that the f of x is greater than k. Oh, hold on a second. Here. There we go. That makes it much better. Okay, so then, yeah, that makes it more clear. So if we just set these equal to some k value, then case one makes more sense as well. So what we're going to say is, let's say for case two is there exists C in the open interval AB such that f of C is greater than k. Okay, that's the second case. Well, in this case, since f is a continuous function over the closed interval and it's bounded, right? The extreme value theorem says it has an absolute maximum. Right? So since it's continuous over the closed interval, the extreme value theorem says, hey, you must have an extreme maximum. Okay, so let's do that. Since f is continuous over the closed interval AB, closed bounded, let's just write that, because it's obviously bounded, is continuous over the closed bounded interval AB, the extreme value theorem says there must exist an absolute maximum. Okay? Now, so also if there is a point in the interval, in the open interval, such that f of x is greater than k, the absolute maximum is greater than k. Right? So since there is a point in A comma B where f, let me see here. Do I want to say that? Hold on. Let's write it. Since there's a point x in the open interval A comma B, such that f of x is greater than k, there, hold on a second. So, since there is a point x in the interval AB such that f of x is equal greater than k, the there you go. Yeah, the absolute maximum has to be greater than k. Okay, that makes sense, right? So in this case here, since we're saying there exists a C in the open interval such that f of c is greater than k, since f is continuous over the closed bounded interval ab, the extreme value theorem says there must exist an absolute maximum in the interval, right? Since there is a point x in the open interval such that f of x is greater than k, then the absolute max must be greater than k, right? All right, that makes sense. So that means, guess what? That means no. I'll say, hence, the absolute maximum occurs at an interior point in the open interval AB. C. Well, let's just put it, let's make this C an element of the open interval AB. Now guess what? Because f has a maximum at an interior point C, and f is differentiable at C, by Fermat's theorem, f prime of C must equal 0. So because how do I want to say this? So because f has a maximum at C in a B, and f is differentiable over the open interval AB, Fermat's theorem says f prime of C must equal 0. And that takes care of case 2. Now, what about case 3? Let's write that down. I'm going to erase this. Make sure you write all this down. Okay, so what's case 3? Well, case 3 is, well, what if there's a value that's less than k? Okay, that's case 3. So case 3 says there exists a C in the interval AB such that f of x is, hold on, not C, x. So there exists an x in AB such that f of x is less than k. Okay. So now that's case 3. Now again, it's very similar to case 2. Okay, so it's analogous. So in this case, case 3 is analogous to case 2 with maximum, right? So with maximum, replaced with minimum. And that's it. And that's the proof to Rolle's theorem. Have a great day.